Welcome to the Ada Lovelace Day podcast. I'm Sue Charman-Anderson, and this month we talk to Kristen Salzer-Frost about the relatively new discipline of fire engineering. And we'll find out all about neuropsychologist Dr Brenda Milner from Nicole George and Cordon Purcell, who together host the Superwomen in Science podcast. Our discovery of the month is a bit of a blast from the past, although surprisingly it's an invention that is still going strong. Yes, this month we are taking a look at the history of liquid paper. But before we get cracking with all of that, I am so excited to announce that tickets for this year's Ada Lovelace Day Live are on sale now. Our annual STEM Cabaret will be held this year on the evening of the 10th of October at the Royal Institution in London. We have an awesome lineup for you with talks on robotics, osteoarchaeology, chemical engineering and a whole lot more. Early bird tickets are just £10 and they are on sale until the 12th of September or until they're all sold out, which might well happen first. You can find out more on our website at findingada.com and you can buy tickets on Eventbrite. We have links to everything in the show notes, of course, but if you really want to cut to the chase, just search for Ada Lovelace Day on eventbrite.com. See you there. So I'd like to welcome to the podcast Kristen Salzer-Frost, who is a lecturer in fire engineering at Glasgow Caledonian University. Hi, Kristen.
Hi, Sue.
It's great to have you on the podcast.
Thank you.
So I think probably the first question that is on everyone's mind who's listening is, what is fire engineering?
It is solving problems to do with fire, usually in the built environment. So buildings, sports stadia, hospitals, schools, sort of anything that's a building, for a very generous definition of building, and has people in it that we want to keep safe from fire. And also perhaps property protection. So even things like data centres where you might not have people there, you still want to protect it in case of a fire.
So this is about sort of making buildings safe and reducing fire risk.
That's right, yeah. So there's building regulations and guidance for whatever it is you're building to make sure that you minimise the risk of fire and to provide a decent level of protection if a fire does break out. And most of what fire engineering is about doing something different to the guidance. It's when the architect, for example, wants to get creative, or you have a new or innovative material that you want to use, and anything that's not covered by the existing standards, that's when you need a fire engineer.
Right. So it's kind of going beyond the detail of the regulation, because I would imagine the regulations probably sort of like minimum standards, and maybe minimum standards are not always good enough.
Exactly right, yeah. The building regulations are definitely minimum standards, and they're also reactive in terms of they only really get updated when something goes wrong and we change the regulations to make sure that doesn't happen again. So some of fire engineering is trying to be proactive so that we can use innovative designs and materials and techniques and use them in a safe manner without having to wait for the regulations to catch up to a disaster.
Yes, that makes a huge amount of sense. And also reassuring, I think, that people are looking ahead to try and understand what new materials do. So I guess the other thing that comes to mind with the term fire engineering is that engineering is one of those words with like a really broad application now. So an engineer is anybody from someone who's writing software to someone who's building the shard. It's quite a broad word. So what kind of engineering is fire engineering?
For me, engineering just means solving problems. And the kind of engineer you are is the kind of problems you like to solve. So structural engineer solves problems to do with structures. So I'm a fire engineer and I solve problems to do with fires. It's a fairly interdisciplinary subject because lots of different areas sort of feed into how a fire would work. So you need some chemistry for how the combustion process works. You need some physics for the transfer of heat and the fluid motion of the smoke. You need some material science for what the building is made out of, how it will react, will it burn, will it melt, will it stand at those temperatures. Even things like psychology can come into it when you're looking at human behaviour and what people do in a fire scenario. So it's sort of taking bits of lots of different things, but as they relate to fire, to solve specific problems.
Wow. So that must mean you collaborate with a lot of people from different disciplines and different areas?
Yes, very much. Usually you'd be part of a design team, so you'd have everyone from an architect, mechanical engineer, structural engineer, even things like the landscape design needs to be considered, because you need to think about where people will go when they've evacuated a building and how the fire brigade are going to get in. So it really does take collaboration with sort of all sorts of people to make a project work.
You know, it's kind of interesting because I never would have thought actually that the landscaping is important. But as soon as you say it, well, of course it's important. Of course there needs to be like a clear area for people to evacuate to and easy access for the fire services. I'm going to draw a slight parallel here to geology, which is what I studied at university. And I remember one of our earliest lectures was a lecturer making the point that geology is quite often about stating the obvious. That when you pick up a rock, it's heavy, that means it's dense, it's dark in colour, that has a meaning too. It's probably volcanic, is it crystalline? Stating the obvious was something that, people, as first year students, we felt sort of unable to do because we didn't want to look stupid. And I'm kind of getting a bit of a sense that actually some of what fire engineering is stating the obvious that can very easily be overlooked.
Yeah, that's exactly. I mean, a lot of it, on some projects, especially if it's a fairly sort of standard design or if it's similar to what the team has done before, you can feel it's all really obvious, but it's just those little things that are so important and somebody needs to make sure those details aren't missed.
I think some of this sounds like it's about also thinking laterally and addressing some of the issues that in hindsight should have been clear, but maybe when you're planning a project aren't.
Yeah, I mean, it's very easy when you're working on a project to go back to your desk and get very caught up in what you need to happen in the project. It can be easy to go along designing something weird and wonderful that worked great for you, but doesn't work very well for someone else. So that constant collaboration is really important. And yeah, sometimes it is the obvious. So especially when there's competing requirements. So for example, I might be trying to keep smoke contained if there's a fire so that people in other parts of the building have plenty of time to get out safely, whereas the mechanical engineer might be trying to get good airflow through the building to ensure that there's, fresh air for people to breathe as they use the building every day. They're both important requirements and they can both be opposing if you don't work together and try and get the details sorted out.
Sounds like there might be a bit of a conflict there between sort of fire safety and the new environmental building standards.
Yeah, actually, one of the things that I've noticed changing a lot in the last sort of 10 years or so is as buildings become more sustainable, it's presented some really new challenges for how you deal with fire in a building. So things like natural ventilation is very desirable in a sustainable building, but it can make smoke control very difficult. And there's new materials that people are trying to use. So, there's a bit of a trend towards timber, which is great for sustainability, but can obviously present new challenges if your building is built out of something combustible. And that's something that is also not very well covered by the building standards in most countries, because as I say, they're usually a reaction. And there hasn't been a big disaster in a sustainable building like that to get the regulations to catch up. So there is quite a lot of work there trying to make these new priorities work with the built environment.
Wow. So, I mean, what kind of changes do you find yourself making to building plans? I mean, which areas do you find yourself focusing on the most?
So there's sort of three parts to fire engineering. There is how the fire is going to develop and where the smoke is going to go. So in that sort of case, you can make suggestions about what materials they're using or perhaps treatments that could be applied to materials to reduce their combustibility. And then also things like what's going to happen to the smoke, where it's going to go. Do you want to vent it? Do you want to contain it? There are different strategies you can take into account. You also need to look at the people and what they're going to do. So that's combinations of things from what sort of alarm system you're going to provide, what sort of drills that the people should have once the building's operational. Obviously, something like a hospital is going to have very different responses to a school. Both of them are quite well organised environments, but what you need to do to keep everybody safe can be very different. So you've got to think about that as well. And then you also need to think about the structure of the building. And this is where there's some crossover with the structural engineer. So often we can provide a scenario of what sort of things the building might need to withstand to enable them to do more specific calculations to the particular building.
Interesting. So, I mean, it does sound really actually quite complex.
Yeah, it can be. Sometimes it depends on how much we know about a various phenomena. So some of the calculations we can do can be really simplistic. How fast do people walk? What's the distance? How long is it going to take them? But then some of them can be hugely complicated once you start including human behaviour factors, or if you're looking at computational fluid dynamics to work out what all the smoke flows are going to be. Yeah, there's a huge range of complexity, and it all comes down really to how much we know about the various phenomena, because we know more about some things than others.
Wow. Before we started emailing, I'd never even heard of fire engineering. So it sounds like it's a new discipline.
I think it is fairly new. I think sort of after the Second World War and then into the 60s and 70s, research into fire sort of grew fairly quickly. And then we started seeing the application of that science sort of in the 90s, perhaps. The first countries started introducing what we call performance-based building codes. And that's really what allows fire engineering to fit within the legislative framework. So it just sort of says you can follow rules A, B, and C to get a safe building, or you can get a fire engineer to show that your building will provide enough time for escape and will, not collapse. And it comes up with sort of functional standards, and you can show that your building meets those standards, and that's something that's allowable to be approved. So, as I say, since the 90s were the first sort of performance-based building codes, and then various countries have adopted them as time goes on. So in Scotland, where I'm based, it was, I think, 2003 when they first introduced the Building Scotland Act that would pave the way for fire engineering to become more of a discipline.
Wow. So, I mean, I think when I was considering what degree to do, the thing uppermost in my mind when I was a teenager was I wanted to do something new and exciting. This really does sound quite new and exciting.
I hadn't actually heard of fire engineering until I got a job with a company that did fire engineering. So I started out studying mechatronics, which is sort of automation and embedded systems. So there's a bit of programming, a bit of mechanical, a bit of electrical. And I got a summer placement writing some software for a fire engineering company. And then sort of at the end of that project, they asked me to stay on part-time and started training me to be a fire engineer. And once I graduated my undergraduate, they took me on full-time and put me through a master's. And yeah, I've sort of gone from there, which has been great. But yeah, as I said, I'd never even heard of it until I got this job at this company. I was just emailing anyone and everyone trying to get a summer placement. Yeah, it is new and exciting, and well, fire is exciting. So because it is so new, there's no sort of obvious route for people to take to get into the subject.
It's funny, I think we often consider careers to be this very linear, well-planned, well-considered progression, and that's, the more I talk to people, the more I realise that there is actually a huge element of luck involved in most people's careers, from the luck of certain technologies being developed to allow certain careers to exist. I mean, like, a lot of my tech career wouldn't exist if the technology didn't exist, and I think it's quite important to recognise the part that dumb luck can play.
Yeah, absolutely. Yeah, I'm sure I left school and I thought, well, I'll go to university and then I'll get a job in what I've studied and then I'll work at that job and get some promotions and eventually I'll retire. And it just doesn't work like that at all. It feels like my career has sort of zigzagged a bit, but really part of that is just being open to opportunities and trying things out and seeing where it takes me. And so far I've been quite lucky. I've enjoyed everywhere it's taken me, whether it's from mechatronics into fire or moving from Australia to Scotland and going from industry back into academia. It's all worked out quite well for me, but none of it has been the plan, I guess you'd say.
And so sort of studying mechatronics, I mean, that must involve a fair amount of programming. That's something I'm also sort of noticing is there's a lot of different disciplines like botany or ichthyology or astrophysics require some degree of programming. I'm guessing you talked a bit about modelling. There must be quite a lot of programming in fire engineering.
Yeah, there can be. So as I say, I got into it by doing a summer project, doing some programming for a company, and I do a lot of computer modelling. And so, when it comes down to it, things like my PhD is mostly computer programming. It is programming a model of, or at least parts of a model of evacuation and CFD, the computational fluid dynamics, which we use for smoke and heat movement. So yeah, there's always sort of this undercurrent of programming to apply to what we need to do. It certainly has enabled most of my changes as well. So going from mechatronics to fire was programming, going from industry to academia was programming, and then having that added experience on how it's going to be applied and being able to look at what I'm doing and see whether or not it will be effective for its purpose has been really useful as well.
Yeah, and I can imagine as well that the development in modelling technologies must have quite a huge impact on what you can actually achieve. I mean, just like raw computing power is really required for some of these big models that we can actually run now, whereas 10, 15 years ago maybe we just didn't have the computing firepower to do that level of complexity. I mean, I know fluid dynamics is really, really complicated and computationally complicated as well. So are you finding that as the technology develops, you're actually being able to sort of really tackle problems that you couldn't have dealt with before?
Yeah, very much. So back when I started, the computer technology wasn't really enough to allow CFD to be used on practical projects. The amount of computing resources that would be required just to do, a few rooms was just not available. But as time goes on, it's become more and more feasible, but we're still butting up against the edge of what's computing resources are available. So if I want to model a whole shopping centre, I couldn't have done that 15 years ago. It just wouldn't have been contemplated. Whereas now I can do part of it, but of course we still don't have the resources to do the whole thing, and it can still take models several weeks to run, which is a long time when you're talking about real world projects and trying to keep the project manager happy.
So what do you think? What are the biggest challenges that you face in fire engineering?
Partly it's getting the rest of the design team to understand where the fire engineer fits in. So a lot of people won't have worked with a fire engineer before. If they've only worked on buildings that have complied with the prescriptive regulations, they may not have had a fire engineer on the team before. And so often they won't have that foresight of where my needs and their needs might clash and where we need to talk to each other early to make sure things work out. So that's one of the hardest things, is because it's so new, everybody that you have to work with is just still finding their feet on how everything fits together.
And I guess as well, people have the assumption that because they are familiar with fire, that they understand fire.
Yeah, people actually have some really big misconceptions about fire, and so they think they know fire, they cook with fire, they might have a bonfire at the beach, but sort of a fire that's sort of raging out of control in a building is a really different scenario. So they take a lot of what they know from, say, TV or movies, and a real fire doesn't work very well in a movie because there's just so much smoke, there's not much to see. So people vastly underestimate how much smoke would be produced. And the smoke is actually what kills a lot of people in fires rather than the fire itself. And people just don't realise how much they'll be because they don't put it into the movies. They also don't realise how quickly a fire can grow. So often you'll see in a TV show, for example, or maybe somebody in a room that's on fire, and they can be standing around in there having a conversation. Whereas in reality, that hot room can go from one item on fire to everything in the room on fire and not survivable within 30 seconds. And so that gives people a false sense of security that they'd be able to get out if there's a fire. Even things like you see people waking up because they smell smoke, and that actually doesn't happen. Smoke makes people sleepy. So if you don't have a smoke alarm to wake you up, most people will just stay asleep and never wake up.
So we really do have to keep our smoke alarms tested and with fresh batteries in.
Absolutely. They are the only thing between you and dying if your house has a fire.
You've talked a little bit about sort of how building designs, how you're improving them to improve fire safety. This kind of makes me think as well about, fire suppression, which must also be a fairly big part of what you're doing, that it's not just about preventing the fires from catching hold, it's also about, if they do, making sure that they are the smallest possible fire.
Yes, definitely. Suppression systems are definitely one of the big tools in our toolbox, although there's a lot of misconception about them too, which can create difficulties when you're trying to convince a client that a sprinkler system would be beneficial for their building. And they've got an image in their head of, James Bond sending off a smoke detector with his lighter and all the sprinklers in the building go off and everybody gets drenched. And that's actually not how they work. The sprinklers only activate by heat from the fire directly acting upon the sprinkler head. So only bits of the building that are already on fire would get water applied. And sprinklers actually use about 10 times less water than the fire brigade do to put out the fire. So in terms of water damage, you're actually better off with sprinklers often as well. And they're not going to be right for every building, but sometimes, it can be a bit of an uphill battle to convince someone that sprinklers would be a good addition to their building, especially if they're not required by the prescriptive guidance. But you can then use the added safety that you get from having those sprinklers to be more innovative and creative in other areas.
So, in terms of the future for you, what's coming up? What are you excited about?
One of the nice things about the ever-increasing computer resources is that my computer modelling becoming more and more possibilities become available. So I think that's going to continue, especially to be part of what I do, because I really love the computer modelling. And also just as they come up with new innovative stuff and new creative ways to think about it, and we know more about what makes a building enjoyable for people to live in and work in, getting to make the built environment a nicer, more people-focused space is something that I'm really quite excited about.
And if there's someone listening who thinks, this sounds interesting. I mean, we've already discussed about this relatively new field. There aren't necessarily any sort of direct pathways into fire engineering. But if someone was really thinking about, this sounds interesting, what kind of skills do they need, and how can they get engaged?
Yeah, well, there are, unlike when I started out, there are now a few degrees in fire engineering that you can study. So if someone's coming out of school, they can actually apply directly to go into a degree in fire engineering. There's also a lot of people who change careers into fire engineering. They might be doing something related, so they might have been installing sprinkler systems, and then they want to go and do some more education and learn about how to design things as well. Or other engineers from other disciplines often move across, so structural engineers or mechanical engineers find that they're being drawn to the fire problems and then start learning about the other aspects that go with it. Because it is so new and because it is so multidisciplinary, people can move in from a lot of different areas. So having a psychology background is useful for the human behaviour, or having a chemistry background is useful for combustion chemistry. So there's a lot of ways into it, even if it's not obvious to start with.
Fantastic. And I think from what you've been saying, it's a career that you would encourage people to pursue.
Yeah, definitely. I've certainly enjoyed it. I like that I can see a tangible difference in the buildings that we work on. I like that it's taken me all over the world. I've worked on projects in so many different countries, from Russia, Malaysia, Italy, all over the place, the Middle East. It's just one of those areas that's, partly because it's so young, there's quite a lot of scope for sort of creativity, and I think that's a really exciting way to work.
Fantastic. It's been brilliant talking to you. It's been both fascinating and educational. So thank you so much, Kristen.
Thank you very much for having me.
Thanks to Kristen for a fascinating look inside the world of fire engineering. As usual, you can find out more about Kristen on our website. Our podcast is made possible thanks to the generous support of ARM, our exclusive semiconductor industry sponsor. You can find out more about ARM's energy-efficient microprocessor technology on their website at arm.com, and you can follow them on Twitter at ARM Holdings. Now it's time to turn our attention to an invention that was very definitely of its time. Back in the 1950s, the business world was at the beginning of a very slow revolution, the 30-year shift from manual to electric typewriters. But as often happens, new technology brings new problems. Manual typewriters use an inked ribbon, and if you make a mistake, a pencil eraser works well enough to let you correct the error and move on. But electric typewriters use carbon film, and using an eraser on that just makes a great big mess. Just one mistake can ruin an important document, something that Bette Nesmith Graham, an executive secretary at the Texas Bank and Trust, knew only too well. She became determined to find a solution, and in 1951 she had a moment of inspiration. With lettering, she said, an artist never corrects by erasing, but always paints over the error. So I decided to use what artists use. I put some tempera water-based paint in a bottle and took my watercolour brush to the office. I used that to correct my mistakes. For 5 years, Nesmith Graham used her correction fluid at work, and although her bosses weren't always happy about it, her co-workers loved it and were constantly asking if she could make them some. In 1956, she started marketing Mistake Out to fellow typists, selling about 100 bottles a month. Her son Michael, who would later become famous as a member of the Monkees, and his friends would help her fill the orders. With a little help from Michael's chemistry teacher, an office supply dealer, and an employee of a paint manufacturer, Nesmith Graham continued to refine the formula, eventually renaming it liquid paper. She worked nights and weekends in her kitchen and garage to make small batches, whilst keeping her day job going. Until, that is, she was fired for accidentally typing the name of her own company instead of the name of her employer's on a piece of important correspondence. Nesmith Graham expanded production when an office trade magazine mentioned her product, and she got a wave of 500 orders from across the US. Then General Electric placed her first large order for 400 bottles. Soon she moved production out of her kitchen and into a portable metal shed in her garden. By 1964, she'd gone from making 500 bottles a week to 5,000. And 2 years later, the business had grown so big that she needed to move into a factory which produced 10,000 bottles per day. By 1970, Nesmith Graham had sold 5 million bottles of liquid paper, and by 1975 she had to expand her factory again, moving into brand new headquarters. Believing that businesses should take better care of their employees, her HQ included an employee library and a childcare centre. The Liquid Paper Corporation was employing 200 people and shipping 25 million bottles a year when Nesmith Graham sold it to the Gillette Corporation for $47.5 million plus royalties in 1979. The Gillette Corporation then sold liquid paper onto Newell Rubbermaid in 2000. And despite the fact that typewriters are mostly collector's items now, people still need a way to correct errors on paper, and a variety of correction fluids, tapes and pens are still sold under the Liquid Paper brand. So the next time you find yourself painting a tiny white patch on a piece of paper to correct a mistake, say a little thank you to Bette Nesmith Graham. So I would love to welcome to the programme Nicole George and Cordon Purcell of the Superwomen in Science podcast. Hi Nicole, hi Cordon.
Hello.
Hi.
I've never actually done an interview with two people before, so I'm not sure listeners won't know who's who. So Nicole, hi.
Hello.
And Cordon?
Hi.
Great. Fantastic. Right. I think we know who you are now, which is fabulous. So you have picked between you a person that you want to tell us about, someone that I had never heard of. Who are you going to be telling us about this month?
So we've chosen to talk about Dr. Brenda Milner.
What kind of a doctor is Dr. Brenda Milner? What does she do?
So Dr. Brenda Milner, she's a neuroscientist and I guess background as well in experimental psychology. And she's actually known as like the mother of neuropsychology. So she's a huge name in cognitive neuroscience, mainly based off of like her groundbreaking work she has with this amnesic patient, HM. And so another just really cool thing that we both love about her, so she's currently 99 years old. She's still an active professor. She's not emeritus, like she's still researching and supervising postdocs at the Montreal Neurological Institute, which is where I go. I'm a neuroscience graduate student at McGill in Montreal. And so, yeah, she's a wonderful person, an incredible researcher, and we're both really excited to talk about her today.
Wow. I mean, still researching at 99, I think that is amazing. That really is.
Yeah, they just had like a birthday party for her yesterday at the M&I. So her birthday was actually in July, but we celebrated yesterday and it was great.
Fantastic. So she clearly has had a very long career. So career achievements is going to be hard to keep that short, I would imagine.
Yeah. So she's really well known for, like Nicole said, her work with this amnesic patient HM. So the results of her research were actually published in 1957. And it's become one of the most cited publications in neuroscience. And HM is really taught in all intro to psych, cognitive psych, and neuropsychology classes. So she worked with him for over 30 years. And through her work with him, discovered that the human brain has multiple memory systems that govern different functions. So the main thing they learned with HM is that he could learn a new skill. I'm pretty sure he learned how to juggle. And day to day, he would improve his juggling skills. But every day, if you asked him, oh, like, why don't we juggle? He would say, oh, I don't know how to juggle. I never learned how to juggle. So really understanding that parts of your brain can remember things while other parts don't remember the exact same thing. So
and actually, you know, that going back to the 1950s, I mean, this work, quite often I end up talking about women who are actually working on foundational research in their field, and this sounds like Milner is another scientist who really sort of set the groundwork.
Oh, absolutely. I mean, like her work on discovering that there's two different memory systems, I mean, that's like the foundational understanding still today of like how memory works. And it really like opened the door into kind of just in general our understanding about the brain, and then a new way to ask questions about like what parts of brains, like structure and function kind of relationships. So absolutely foundational.
So when you talk about two different memory systems, are we talking sort of long-term and short-term memory?
her work was more on different parts of the brain. So not necessarily just long-term and short-term, but parts of the brain that would remember the motor movement for something versus the cognitive part of the brain that remembers that you know that thing. Procedural memory is like kind of like known, memorized movements. So you learn how to ride a bike and you always know how to ride a bike. And then episodic is remembering the steps to ride a bike.
So what was then, I mean, she did this groundbreaking work, you know, what's the impact of that? Like, how has that affected the neuroscience and neuropsychology since then?
I guess we touched on this a bit before, but I mean, it really did lead to this creation of this new field of cognitive neuroscience because she combined, or her work combined neurology as well as psychology.
Okay, so you mentioned that Milner was working with this patient HM. Can you tell us a little bit more about him and why he was important?
Yeah, so HM, he was actually a patient who had epilepsy, and he elected to have a surgery done, so surgery to his medial temporal lobe, and it was actually bilaterally as well. And then that led to having these memory difficulties. And so at the time, Milner was working with Dr. Wilder Penfield, who was also a huge name in neuroscience. And so they had a couple amnesiac patients post-surgery kind of come their way.
So they started working with HM, and it really led to all of these different discoveries on what parts of the brain really store and work in memories, and how it's not just one single focus of the brain. He really helped lead to all of these different understandings of how the brain works with memory.
Yeah, and I mean, Brenda did it was meticulous testing. She worked with him for 30 years of doing all sorts of different tests to really differentiate and really figure out all of the effects of post-surgery and the effect of damage on the brain.
Wow, I mean, it's an amazing thought to think that she worked with the same patient for so long.
And that he had amnesia, so he didn't remember her at all in the 30 years of working with her.
Oh, wow. That must have been really hard, actually. I can imagine that you're going into work each day and every day you've got to introduce yourself anew. That must be tough.
Yeah, I can't imagine that.
So what is it about Milner that really chimes with you? What do you find inspiring about her?
One thing that kind of particularly sticks out about her is just her openness towards scientific inquiry. I actually was watching this interview of her on YouTube. She was describing how when she first started working with Dr. Penfield, she was working strictly in neurology, but then patients were complaining that post-surgery they were having memory problems. And so she decided then that she wasn't just going to say to the patients, no, I'm not studying memory, I'm here to study neurology, and just forget about it. Instead, she said, if people are complaining about this must be an important question to research, and I want to study that. And then she switched her focus, which some people have also said was kind of risk-taking. It wasn't a popular topic at the time. They said it would have been a lot better to just stick with what she was doing with her supervisor. So I think that that's very inspiring.
Obviously working until the age of 99 and still providing so much to her field of science is just amazing and so inspiring.
Yeah, imagine staying on top of the literature she's been working for almost 70 years. That's crazy, just to be so relevant and to still continually be so interested. And she did. There was a New York Times piece that just came out last year that they interviewed her, and she was just I'm not emeritus. I've still got questions to ask. I'm still curious. I'm still nosy. And that's so cool.
It's really interesting for me because I'm a music therapist, so I have a lot of psychology in my background and in my training. And one of my favorite classes was neuropsych classes, and I loved learning about memory, which parts of the brain affect memory, but I never heard the name Brenda Milner. In all of my intro to psych classes and all of my training, I heard about HM, and I learned about him a lot, but I never heard her name. So I think it's really great for me to connect all of these dots and to finally know that it was this amazing, strong woman who really made all of these breakthroughs and really pioneered a field that I'm very interested in, the field of neuropsychology.
And actually it's not an uncommon story that, we hear about women's discoveries and their work, but we don't hear their names. So at what point did you find out about Milner and sort of join the dots and say, oh, right, that's this HM that I've been studying about?
Probably in the past year, Nicole and I were talking about different things when we were both at school in Montreal, and she brought up Dr. Milner and, there's this 98-year-old woman who's still doing research on my campus, and started to really learn about her and really figure out that, oh, I know her and I know her work and I know a lot of the things that she really grounded and started. So probably in the last year, which is really sad.
And it was probably like, for me, it just came out because I'm now attending McGill, which is where she is. And McGill is really great about really promoting Brenda as a professor. But same thing. I would read these textbooks in my undergrad, all about HM and stuff. And then I got here and I was like, oh my God, I didn't know that this was 99-year-old professor. That's amazing.
It is absolutely astonishing. And I think as well, the fact that it's not just that she is, 99 and still curious, the fact that she's still doing research and still working with PhD students. It's just absolutely awe-inspiring. I am totally in awe of her. So, in terms of other aspects of her work, are there other parts of her career that are influential as well?
So along with memory, Dr. Milner also did a lot of research on language and language processing in the brain. So language is another process that people really believed that was central to a certain area or to certain areas in the brain. But really, language and memory function is processed all over. She did a lot of PET scans, MRI scans to find the different brain regions involved in language processing in uni and bilingual participants. And she also works with patients with brain lesions in these areas to see how language is affected, which again is something I learned about in my undergrad, but never knew that she really worked in.
So this is in part as well, because as a left-handed person, I remember reading books when I was younger about how the left-handed brain is different. And one of the things that would always come up in articles and books and that, it's like, oh yeah, the speech centers are in different places in left-handed people. That's what she was working on, right?
Yeah, and also just finding places outside of the typical language centers of the Broca and Wernicke's areas.
Well, I think just to add on to that as well, not only is she's really influential in the research that she's done, but she's a really great science communicator as well. I was watching a TED Talk. Actually, I think it's an affiliated TED Talk because it was at the campus, where she was talking about the effects of bilingualism. And it was just a really great talk where it was very much more about relating to people and languages as a builder of bridges across cultures. And it's just fascinating to me that she's such a dynamic voice within neuroscience and neuropsychology, but she's also extremely good at being a relatable, well communicated scientist to the public. And another way that she's a wonderful researcher.
She is definitely someone that I want to go and read up on and find out a lot more about. So thank you both so much for introducing me to Dr. Brenda Milner. I hope that I hit 99 and I'm still going as strong as she is. She is amazing.
Oh yeah.
Well, thank you so much, both of you, for being on the podcast, and I look forward actually to listening to your next episode of Superwomen in Science, and I will of course put links in the show notes for everyone. Thanks to Cordon and Nicole for their time this month. You can find the Superwomen in Science podcast online at superwomeninscience.wordpress.com, and they are, like us, on SoundCloud and iTunes. Links, as usual, are in the show notes. You can also follow them on Twitter at SuperwomenSci, and they're on Facebook too, at facebook.com/superwomensci. So please do give them a listen, and give a little social media love to my fellow Women in STEM podcasters. Thanks again to our sponsor, ARM, for their ongoing support, and thanks also to our editor, Andrew Marks. Don't forget that you can subscribe to our podcast on SoundCloud, iTunes, Google Play, and Stitcher. And if you like what you hear, please share it with your friends. And of course, don't forget to buy your tickets to Ada Lovelace Day Live. You can find information about our speakers and the venue at findingada.com, or just search for Ada Lovelace Day on eventbrite.com. In our next episode, we'll be talking to Dr. Marianne Maria-Selvum about getting medical innovations into hospitals where they can help save lives. So, thanks for listening, and we'll catch you next month.